Good evening, everyone. Welcome to the Geological Society. I'm Richard Hughes, and it's my pleasure to welcome you to this public lecture this evening. Just before we invite the speaker up to the podium, could I just ask you all to make sure that your various devices are either turned off or put onto silent mode? Thank you. And also just to make you aware, we have no fire drills practice for the evening. You'll be pleased to hear. So if you do hear an alarm, we will need to evacuate the building. And for those of you near the front, the nearest exit is through here into the Burlington House courtyard. And for those of you right at the back, you will need to exit through the door you entered through onto Piccadilly and muster in the courtyard. Hopefully this will not be necessary. So on to the main event. This society has designated 2019 our year of carbon. And as part of this year's themed activities, I'm taking great pleasure this evening to welcome Professor Carrie Lear, who is going to deliver her lecture this evening entitled The Big Antarctic Freeze. To give you a little bit of background, studying changing sea ice allows Earth scientists to understand its interplay with paleoclimate and helps us to predict how it may respond to climate uncertainty in the future. And the future loss of ice on Antarctica, being the world's biggest ice sheet, of course, represents the largest uncertainty for predictions of future global sea level. Melting of the oceans has contributed a fairly minuscule 8 millimetres to global sea level rise since 1992. But 40% of that has taken place in the last 4 years, since 2015. But the water contained within the Antarctic ice sheet is enough to increase global sea levels, if it all melted, by a staggering 65 metres. This evening, Carrie is going to explain to us how scientists reconstruct changes in Antarctic ice sheet volume back through geological time, discussing the implications of ice sheet formation on geochemical proxy records. They tell the surprisingly dynamic story of the Antarctic ice sheet with concerning implications for ice sheet stability into the future. Carrie studied for her undergraduate degree in Earth Sciences at the University of Oxford before obtaining her PhD from the University of Cambridge. Carrie has been a research associate at Rutgers University in New Jersey before returning to the UK to take up her current post as a lecturer within the School of Earth and Ocean Sciences at Cardiff University in 2004, where she's now a Professor of Earth Science. Carrie's part of the Ocean and Climate Systems Research Group, with a particular interest in geochemical proxies and paleoclimatology. She was awarded the Bixby Medal of this Society in 2017. So please join me in welcoming Carrie to the stage.
Thanks so much for that introduction, and thank you everyone for turning up, especially on such a lovely day today. So, the big Antarctic freeze. Okay, I want to start by putting this into context. So, in 1958, Dave Keeling started to measure the concentration of carbon dioxide in the atmosphere at Mauna Loa Observatory in Hawaii. And when he started these measurements, CO2 concentrations were 315 parts per million, and today, because of burning of fossil fuels, they are over 400 parts per million. And of course, we've known about the greenhouse gas properties of carbon dioxide since the 1850s, so this inexorable increase led to the formation of the Intergovernmental Panel of Climate Change, IPCC, in the late 1980s. And the IPCC have produced these assessment reports regularly, and these have played a really important role in raising the awareness of the problems of climate change with both the public and also policymakers. But as you can see, they've yet to make a dent on this Keeling curve. So CO2 concentrations are increasing and our climate is warming. And because we live in a warming climate, our sea levels are rising. And they're rising for two reasons. The first is because as the oceans warm, they expand. And the second is that around the world, glaciers are melting and our ice sheets are melting, the Greenland ice sheet and the Antarctic ice sheet. So, for example, this image shows the Antarctic ice sheet, and you can see some areas in blue. This is where the ice sheet is gaining mass due to increased snowfall, but these areas are far outweighed by the areas of the ice sheet currently losing mass in red. So on average, the Antarctic ice sheet is losing about 125 gigatons of ice every year. And, you know, as we just heard, this is concerning because our ice sheets, the Greenland ice sheet and the Antarctic ice sheet, they contain enough water within them that if they were to melt, globally sea levels would rise about 70 metres. So that's the height of Westminster Abbey. So we know from satellite measurements that sea levels are rising. They're currently rising about 3.5 millimetres every year, which is the width of my favourite biscuit. And I can testify that these stack up pretty quickly. But more sobering is actually the acceleration of sea level rise. So just a few decades ago, sea level was rising at about half this rate. So obviously, you know, we're concerned about what is it going to be like in the future. And the IPCC they regularly publish projections of what sea level might look like in the future, and these are based on ice sheet models. But obviously, you know, ice sheet models are basically a set of mathematical equations that are used to describe some quite complex processes occurring in the climate system and also in the ice sheets themselves. And some of these processes, especially these glacial processes, happen so slowly that it's difficult to test the models using modern observational data. But what we can do is test the models using records of climate change from the past. And this is why there's a whole field of research called paleoclimate research. So I'm a paleoclimate scientist. And we reconstruct records of past climate in order to better understand the climate system and, you know, interrogate some of these models. So I'm sure you're all familiar with the idea that climate has changed in the past, and that means that as a scientist, what we can do is basically pretend we're Doctor Who, and we can do a bit of time travelling. We can hop into our TARDIS and go and see what the planet was like at different times in the past. And so I want to take you on a journey with me through time, and our first stop off that we're going to make is 33,000 years ago. And we're going to actually follow in the footsteps of William Buckland, who was president of this society in the 1820s. And William Buckland investigated this cave on the Gower Peninsula in Wales. This is Paverland Cave. And in it, he found a skeleton that had been painted red. And he called it the Red Lady of Paverland. We now know it was a man, but details. We actually thought it was a Roman prostitute because of the red bones, but there you go. It was a male, but also we now know from radiometric dating, a lot older than the Roman times, this skeleton is 33,000 years old. So this skeleton, possibly your great, this many greats grandfather, who knows? So this chap was living 33,000 years ago in a climate that was a lot colder than today. He coexisted with mammoths. In fact, he was found wearing a mammoth ivory necklace and probably hunted these mammoths. So he lived when climate was a lot colder. There were large ice sheets in North America and over much of Europe. And these ice sheets were so large, they locked up so much water from the oceans that sea level was probably over 100 metres lower than today. Because sea level was so much lower than today, Britain wasn't the island that it is today. Britain was just a peninsula of mainland Europe. So, let's hop back into our TARDIS again. And this time we're going to go back even further in time, and we're going to go back 125,000 years. As Earth scientists, we're actually going to stay on the Gower Peninsula, and this time we're going to look at this beach that you can see me standing on here. This is a fossil beach and it sits several metres above the modern beach. So you can just see the modern beach here with the waves crashing on it, and then probably about 5 or 6 metres above that is this fossil beach. And this formed 125,000 years ago when climate was probably quite similar to today, actually. So about 1 degree warmer than pre-industrial climate. And sea levels were probably 6 to 9 metres higher than they are today. Now, this geological outcrop is protected, but I have got a chunk of it here. So I did find this in our very old teaching collections from Cardiff. So I brought it with me, and I encourage you after the talk to come and have a little look at it, because it's a beautiful example of a fossil beach. You can see these lovely rounded pebbles, and then if you look carefully, you can see all these seashells in it. And so this formed when sea level was about 5 or 6 metres higher than today. So we have really strong evidence for quite large changes in climate in the recent geological past, in the Pleistocene. And through the Pleistocene, we know that there were these cycles. There were glaciations and interglaciations, so glacial, interglacial cycles. And these were paced by changes in the Earth's orbit. So the way that our planet orbits the sun changes through time because of the other planets in the solar system. So the effect of gravity from Jupiter and Saturn, for example, that slightly changes our orbit and our wobble and our tilt. That affects the distribution of the incoming solar radiation. That impacts our climate system, but that also sets into place some feedback mechanisms which impact carbon dioxide. So actually these cycles are greatly amplified by changes in this greenhouse gas in carbon dioxide. And if you're an earth scientist studying Pleistocene climate change, you've got this really incredible archive at your disposal, which is the ice cores, ice core records. So these are cores taken in our ice sheets today, and you know, the ice in the ice sheets builds up slowly, year on year. When every winter you have a big snowfall, and that sits on top of the ice sheet, and then it gradually compacts all the snow below, and you end up forming this very solid, massive ice. But inside this ice are tiny trapped bubbles of air. So what we can do is we can get these cores of this ice, and then you can gradually melt them. You can melt them layer by layer by layer. And as you melt them, you pop open these tiny little bubbles of air. And then we can analyse those, and we can determine what the concentration of carbon dioxide was in the past. So this is a direct measurement of the composition of our atmosphere. And we have this continuous record going back 800,000 years. And I'm going to show you what it looks like for the last 400,000 years. So I've got a graph here. This is 400,000 years ago, coming up to modern. And this is the concentration of carbon dioxide in the atmosphere. And you can see that the carbon dioxide concentrations have kind of changed in this very cyclic manner. And we have these cycles that appear roughly every 100,000 years. And as I said, these are paced by these orbital cycles. So this is actually the 100,000-year cycle is the eccentricity cycle, how eccentric our orbit around the sun is. So what we find is that, you know, during the glacial periods, when we have these huge ice sheets in North America and in Europe, for example, this is when carbon dioxide concentration is very low. So they were around about 180, 190 parts per million in all of these glacial periods. And then the interglacial periods, carbon dioxide concentrations are always about 280 parts per million. And we have the same picture going back, you know, the full 800,000 years that we have this record. So the raised beach from the Gower that we looked at, that formed in the last interglacial, so that's about 125,000 years ago. And your possible ancestor, the Red Lady, lived here in a slightly warmer part of the last glacial. So through the Pleistocene then, carbon dioxide concentrations have kind of varied through these rather fixed limits, but then obviously in the last 100 years or so, we've managed to increase carbon dioxide concentrations by more than the glacial interglacial difference. So this rate of forcing is completely unprecedented. We can't find anything as fast as this in the geological record. So what does this mean for our future? And what does this mean for sea level? Well, we can look at what happened in the Pleistocene. So we know, for example, that between the last glacial maximum and the Holocene, sea level rose 120 metres, and it did that at an average rate of 1 metre per century. But that wasn't a continuous, it wasn't a steady increase in sea level. It was kind of, there were intervals when it was faster, intervals when the sea level rise was slower. There were some centuries that saw sea level rise about 5 metres in 100 years. So could this happen in our modern climate? This tells us what the climate system, what the cryosphere is capable of. Should we expect this in the future? Now, one important thing to realise, of course, is that this sea level rise was caused mainly by the collapse of these northern hemisphere ice sheets. And, of course, these don't exist anymore, apart from the Greenland ice sheet. And you can see that these were extending to much lower latitudes than our modern ice sheets. So this is not by any means a direct analogue of what might happen in the future. But what this does do, of course, is give us a huge incentive to understand the Antarctic ice sheet. So this is the largest ice sheet on our planet. As you heard before, alone this has the potential to raise sea levels by about 65 metres. So what I want to do is talk about what we know about the Antarctic ice sheet. How can we determine its history? How can we determine when it formed? Why did it form when it formed? And then after it formed, how sensitive was the Antarctic ice sheet to climate? And so we're going to hop back into the TARDIS, and this time we're going to go way back into geological time, and we're going to go back 50 million years. And at this time in the past, your ancestors looked pretty different. And the planet looked quite different too. I mean, recognisable. We can still recognise the continents here. You can see some of them are in slightly different positions to today, and there's some seaways, open seaways, that don't exist today. But on the whole, it's a fairly recognisable world. One big difference is how green it is. So see, Greenland actually deserves the name Greenland, and Antarctica is vegetated as well. So this is Earth. This is what Earth looked like in its what we call its greenhouse state. So there's hardly any ice on the whole planet, and the climate was much warmer. Sea levels were a lot higher than today. In fact, you can see the seas spilling out onto the continent here. Now, there's lots of fossil evidence that shows how warm the climate was. So this is a fossil nautiloid from National Museum Wales. It was actually collected not far from here. So this is from the London Clay Formation. So 50 million years ago, the UK was a very different place. They had nautiloids, there were sharks and turtles swimming offshore the UK. And in fact, I have brought some Eocene turtle shells with me that were collected from the Isle of Wight. So these are just from some Eocene mud that outcrops on the Isle of Wight. And I'm happy to pass these around if you'd like to have a look and just think about those turtles happily swimming offshore in the UK. So while all these sharks and turtles were swimming around, on land here we had palms and lots of other different tropical plants. And meanwhile, a lot further north, we had forests of beeches in Svalbard and Spitsbergen, where obviously, this doesn't support any trees today. There used to be lush forests, and I've actually brought with me one of these, some of these fossil leaves. So these are Eocene beech leaves collected from Spitsbergen, really nicely preserved. So this is a bit too heavy to pass around, but feel free to come up after the lecture and have a look at this specimen. So, 50 million years ago, then our planet was in this greenhouse state, and at some point in its history, it transitioned into an icehouse state. So as Earth scientists, then we want to know, when did this happen? Why, how and why did it happen? Now, fossils are great, and they build up this really vivid picture of what climate looked like in the past. But I want to talk to you about the sorts of work that I do using geochemical proxies to generate really quantitative records of how climate has changed in the past. And to do this, I use sediments collected from the open oceans by drill ships. So this is the JOIDES Resolution, which is operated by the International Ocean Discovery Programme. And I lived on this boat for 2 months while we cored sediments in the Pacific. And when we bring those sediments up onto the boat, which is a huge technological achievement, actually, because this boat is kind of coring in 4 kilometres water depth, and the waves are going up and down like this. And it's got this 4-kilometre long core barrel that goes right through the middle of the boat to stop it capsizing. It's incredible technology. Anyway, we bring these cores up onto the deck, and when we look in them, we find these amazing fossils, these microfossils. And I've brought some with me again, if you want to come and have a look at these at the end. They kind of just look like tiny little grains of sand here, but if you were to look at them under a microscope, they would look like this. Really beautiful fossils. I've got a little model of one as well here. So each one about the size of a pinhead. Incredible things. They're single-celled organisms. They're a little bit like amoebas, but they make these amazing shells or tests out of calcium carbonate. And these ones are planktonic, so these live in the surface waters of the oceans. These are benthic, so these live on the sea floor. And they act like little time capsules for us, so we can analyse all kinds of things in them. And these tell us about conditions at the top of the oceans, and these tell us about conditions at the bottom of the oceans. So they're made of calcium carbonate, the mineral calcite. This is the same mineral that chalk is made of, the White Cliffs of Dover. In fact, this is pretty much made of microfossils like this, but then also nanofossils. So even smaller fossils of calcareous algae called coccoliths. And you can kind of rub your finger on the chalk, and you're actually rubbing off all these little nanofossils. So, what can we analyse then? What can we measure in these fossils? Well, you can see that the calcium carbonate contains oxygen, and one of the most important proxies that we can measure is the oxygen isotope ratio. So the ratio of the heavy isotope oxygen 18 to the light isotope oxygen 16. Why do we want to do that? Well, the ratio of these two isotopes in our fossils reflects the ratio in the seawater. Okay, so you are what you eat. And to explain why this is useful and important, I need to use my ping pong balls. So I want you to imagine that these ping pong balls are molecules of water making up our oceans. And the blue ping pong balls, this is a molecule of water, H2O, and it contains the heavy isotope of oxygen, oxygen 18. And the white ping pong ball is H2O, and it contains the light isotope of oxygen, oxygen 16. And now we have the sun beating down on the surface of the ocean, and we're going to evaporate some of that water. And we will preferentially evaporate the molecules containing the light isotope of oxygen. So we have this parcel of water then, this water vapour in the atmosphere that's enriched in oxygen 16 relative to the oceans. And some of that water vapour might rain out, and that's going to preferentially rain out the heavy isotope. Oof. Good catch. So our parcel of water vapour gets more and more enriched in the light isotope. If this is transported to higher and higher latitudes, eventually it might fall as snow on Antarctica. So this is Antarctica here, just in case you were wondering. So this process goes on and on. So now let's imagine we're building up an ice sheet through time. So we're taking out all of this fresh water from the oceans and putting it onto the continents. So we're locking it away from the oceans, storing it as continental ice. And you can see that the water that's remaining in the oceans is now enriched in oxygen 18, in that heavy isotope. And this ratio is then recorded in these little shells of these Foraminifera, in this oxygen here. So that's kind of how the oxygen isotope proxy works. It is a little bit more complicated, though, because when the Foraminifera actually precipitate this calcium carbonate, they preferentially use oxygen 18. So in other words, they do fractionate this ratio slightly from seawater, and the degree of fractionation is temperature dependent. So what that means is when we measure the oxygen isotope ratio in the Foraminifera, it's actually telling us two things. It's telling us the temperature of the seawater and also the oxygen isotopic composition of the seawater, or the ice volume, which can lead to problems interpreting your records. However, fortunately, in the same Foraminifera, in the same fossils, we can also measure how much magnesium they take into the calcite. And they do this kind of accidentally without even realizing. But it turns out that if these Foraminifera are living in warmer waters, they take in more magnesium. So we can measure the amount of magnesium, calculate the temperature. That lets us calculate this fractionation effect on the oxygen isotopes, and so we can calculate the oxygen isotopic composition of seawater. So by measuring these two properties of the fossils, we have both the temperature of the oceans and the global ice volume. And actually, there's a whole suite of geochemical proxies that we can measure in these Foraminifera. And I just mentioned one more, which is, a really exciting one that's just been developed in the last decade or so. And this is the boron isotope ratio, because it turns out that this ratio is dependent on the pH of the water. And we can use that to tell us something about carbon dioxide. So if you have more carbon dioxide in the atmosphere, you'll have more dissolved in the surface waters of the oceans, and that will change the pH of the surface oceans. Now, if you didn't get all of that, don't worry. I'm very happy to take questions on it at the end. But the bottom line is that we can put these forams in some fancy mass spectrometers. We can measure a whole bunch of different properties of the Foraminifera, and we can work out what temperature, ice volume, and carbon dioxide was like in the past. Okay, so now I feel like I'm ready to show you some of my marvellous wiggly plots, some of the actual geochemical data. So just to orientate you then, on this y-axis, this is age, so starting at 70 million years ago up to modern. And to put this into context, this is when the non-bird-like dinosaurs went extinct, 65 million years ago, so that's at the Cretaceous-Paleogene boundary. And 3 million years ago, this is when the hominin Lucy was walking the planet. Okay, so we'll start with this temperature plot then. So this is the temperature of the bottom of the oceans through time. And you can see that the temperatures have decreased from about 12 degrees centigrade. So bottom of the ocean is about 4 kilometres water depth. 50 million years ago, they were pretty toasty, 12 degrees centigrade. And they've cooled to probably 1 or 2 degrees that they are today. And this makes complete sense with our understanding of the climate system, because we know that over this time, concentrations of carbon dioxide in the atmosphere have gradually lowered over tens of millions of years. Okay, so that's the temperature record. This is the oxygen isotopic composition of the Foraminifera. And you can see that the shape of these two records looks something similar. But remember, we can actually use these two records together to calculate the oxygen isotopic composition of seawater, which is our ice volume proxy. And so we have larger ice sheets in this direction, smaller ice sheets in this direction. And here's the result, and hopefully you can see that the shape of this record actually doesn't really look much like the shape of this record, our temperature record, which is really interesting. It's telling us something very interesting about the climate system and how the cryosphere interacts with the climate. So whereas the temperature shows this kind of not completely steady, but it does show this quite a long-term cooling trend, the ice volume signal is quite different, and we have a lot of the action, if you like, occurring at certain events in the geological past. And this is the one that I'm going to be focusing on now. This occurred 34 million years ago at the Eocene-Oligocene boundary, and you can see that we have this sudden increase in oxygen isotope composition, so an increase in salinity of the oceans. This is when the Antarctic ice sheet formed. So it turns out it went from being a very small ice sheet to an ice sheet, something quite similar to modern day, relatively quickly. And when I say quickly, I mean quickly for a geologist. So it still took over 100,000 years. So this is Earth's Greenhouse-to-Icehouse transition, and it happened 34 million years ago. So as Earth scientists, of course, we're interested in why did this occur? Why was it then and not some other time? And throughout the last few decades, there have been quite a few different ideas or hypotheses proposed to explain this glaciation event. Back in the 70s, a very popular one was the thermal isolation hypothesis. So Antarctica used to be joined to Australia and South America, and they slowly rifted northwards over time. And as they rifted northwards, that opened up a seaway around Antarctica, and the idea is that that could have cooled the continent. But we now know that the timing's not brilliant. Timing doesn't really explain it very well, and there's been lots of really detailed ocean modelling studies trying to kind of simulate this, and it just seems that the effect is actually not quite big enough to explain this Greenhouse-Icehouse transition. The second mechanism is seasonality. So if we think of what's actually happening on the ground when we start to grow the Antarctic ice sheet, just before it became established, there would have been snow falling in winter, but every summer that snow would have just melted away again. So you were never able to build up glaciers and coalesce them into an ice sheet. So what you actually need to happen on the ground, what this threshold actually is for the snow to persist year round. And for that, you need cooler summers. And one way that you can get cooler summers is to have reduced seasonality. So the extent of our seasonality is determined by this angle of the axis of rotation of the Earth. So, if this was vertical, we wouldn't have any seasons. But it's not vertical, so we do have seasons. So the steeper this angle, the higher the seasonality of our planet is. And of course, there's lots of changes in the way that our planet orbits the sun. So this angle changes. Where that axis of rotation points in space, that changes. The actual shape of Earth's orbit changes as the other planets in our solar system are moving about. And really smart physicists are actually able to calculate these changes incredibly accurately. They can do this for millions of years in the future and tens of millions of years in the past as well. And what we find when we look at these orbital solutions, we find that we compare the orbital solutions to our records of ice volume change. So this is our oxygen isotope proxy. This big step here, this is the Greenhouse-to-Icehouse transition. And this occurred when we had this orbital solution that led to very low, very reduced seasonality, so cooler summers. So it seems that in terms of the exact timing of the event, why did this happen here and not, 100,000 years later or 200,000 years later? That is due to this subtle change in the seasonality of our planet. However, this sort of orbital configuration is repeated throughout geological time, so it occurs every couple of millions of years or so. So on its own, it can't explain the Greenhouse-to-Icehouse transition. It can't explain why it didn't happen 10 million years earlier or 10 million years later. There must be something else in the climate system that preconditioned the system for glaciation. And you can probably see where this is going. So the last and most favoured hypothesis is this idea of a CO2 threshold. So again, we come back to this idea of needing that winter snowfall to persist year-round, so it survives the summer. But instead of surviving the summer because of a change in seasonality, it's surviving the summer because the whole climate of the year round is colder. So we have reduced greenhouse effect. So the idea is that we have this slow decline in carbon dioxide concentrations, gradually cooling the climate, and then you pass this threshold and you can suddenly grow the ice sheet. And this was really nicely demonstrated in this fantastic modelling study by Rob DeConter and Dave Pollard. So these wiggly lines, this is the output of their model, their ice sheet model. The model is forced with very, very slow gradual decline in carbon dioxide, which you can see on this axis here. And we have these just really tiny changes in ice volume, and then boom, we pass this threshold, and geologically, relatively speaking, quickly we grow the ice sheet. And the shape of this looks, very similar to the shape of our proxy records. The records I showed you earlier support this idea. So this is our deep sea temperature record, so we have this gradual cooling of climate, but then once we're past some sort of threshold, we have this rapid increase in ice growth. And then quite recently, we've got some new proxy data for carbon dioxide concentrations, and these show a gradual decline in carbon dioxide concentrations through the late Eocene up to the Greenhouse-Icehouse transition. So we think now that we have a pretty good understanding of why the Antarctic ice sheet formed when it did. So what we're interested in now is, how stable was it subsequently? How sensitive was it to climate? And the answer is, it was actually pretty dynamic, so not very stable. If it was stable, this line would just kind of carry on up here. But you can see we have all these changes in global ice volume. And at first this was really confusing to us, because if you think of the modern day Antarctic ice sheet, it's 4 kilometers thick in the center. It's huge. That top surface, it's really high altitude, really high latitude. It's white, it's shiny. It should be pretty difficult to mount. And it is difficult to mount from the top down. It's very stable once it's formed from the top. But there's been this kind of realization fairly recently that actually, a lot of this ice sheet is interacting with the oceans. So if you were to remove all of the ice on Antarctica, this is what the continent looks like now, because that weight of ice has pushed the continent downwards. So all of these blue areas, these are areas underwater. So this is where the ice sheet is actually sitting on the seabed below sea level. And this means that these areas are quite vulnerable to warming. And we know that the Greenland ice sheet is pretty vulnerable to warming too. It's currently melting, and estimates say that it will completely disintegrate if climate equilibrates probably somewhere between 2 and 3 degrees warmer than pre-industrial. Then that will set that ice sheet off for a complete disintegration. So we can actually add up all of these kind of volumes of ice in these vulnerable areas on the planet. So we've got West Antarctica, East Antarctica, and Greenland. And we come to this kind of estimate of about 30 meters sea level equivalent. Okay, so all of the vulnerable ice on the planet, if that was to melt, sea levels would rise 30 meters. So can we hop into our TARDIS and go into the future and see where sea level is going to end up? Well, it depends which future we choose, actually, as the human race, when I say we. So this figure is from the last IPCC report, and it shows annual emissions of carbon dioxide. So we're currently putting about 50 billion tonnes of carbon dioxide into the atmosphere every year, and this is increasing year on year. Ahead of us, of course, there's all these different possible scenarios that we could follow, depending on how much we get our act together, basically, how much politicians get their act together. So this would be a business as usual scenario. IPCC call that RCP 8.5 because it leads to an additional radiative forcing of 8.5 watts per metre squared. And then we have 6.0, 4.5, 2.6. So to put this in perspective, if climate was going to become stabilised at 1.5 degrees warmer than pre-industrial, we should be following this scenario. This one would probably lead to climate stabilising at about 2 degrees. So it depends how much carbon dioxide we put into the atmosphere. To give you some idea of where we are now, So these are those different kind of stabilised concentrations of carbon dioxide, depending on those different emission scenarios. Each of those obviously will lead to a different amount of climate warming. You know, in the Paris Agreement, most countries around the world signed up to the Paris Agreement that has the aspiration of limiting climate to 1.5 degrees. The pledges actually put down by countries around the world are currently putting us here. So at a warming of the planet of 3 degrees, and the policies actually in place putting us here about 3.3 degrees. So what does this mean for future sea level? Well, I wanted to show you a really interesting study that's just been published in Nature just a couple of weeks ago. These researchers looked at some coastal caves in Mallorca, and they found some tufa deposits in the caves that were deposited at sea level. And this is really great because we can date these really precisely and we can see exactly where they formed. So we can say something about sea level in the past. And these all formed in the Pliocene, which was, you know, fairly warm, and when Lucy was walking around the planet. And what these authors conclude is that if climate is going to stabilise between 2 and 3 degrees, so remember at the moment we're on course for 3 degrees warming, if climate stabilises at 2 to 3 degrees, we can expect global sea level to eventually reach 16 metres higher than modern. If climate stabilises at 4 degrees warmer than pre-industrial, then we can expect a sea level rise of about 23 metres. Now, obviously, that's not going to happen immediately. These ice sheets aren't going to melt overnight. But this does raise a really important problem that I think scientists have in communicating science very often. And I call this the problem of 2100-itis. And this is when we're kind of putting out sea level predictions, we often say, oh, you know, sea level might be this much higher than today at 2100. And the message that after 2100 the sea levels will continue to rise never really seems to get through. It's as if climate change is going to stop at 2100. So we could stabilise climate 3 degrees warmer than today at 2100. Sea levels will continue to rise for hundreds of years because the system's not in equilibrium. And of course, everyone who's ever built a snowman knows that. You build a snowman, the weather warms up, and your snowman just stays there for a little while, but it melts. So what ice sheet models are doing is trying to predict this, but for a much more complicated system. They're trying to predict what the Antarctic ice sheet is going to do in a warming climate. So let's look at some of these processes that these models are trying to capture. This is a useful diagram because it shows the base of the Antarctic ice sheet resting on the seabed below sea level, and it's attached to an ice shelf here. So this part is floating. It's not really part of the true ice sheet. This is the ice sheet, and they're connected at the grounding line here, which is when the ice sheet lifts off the sea floor. And these ice shelves, it turns out, are really important for understanding the Antarctic ice sheet. And that's because in many cases they have this important buttressing effect. So they're stabilising the ice sheet behind. And this was really nicely illustrated in 2002 when the Larsen B ice shelf broke up, and this was captured in these lovely satellite images. These dark lines are pools of meltwater that formed because of the warmer air. And that meltwater, you know, drove down into the ice shelf and cracked it open and made the ice shelf disintegrate. And once it disintegrated, these glaciers behind started flowing to the oceans 8 times faster than before. So when the ice shelves break off themselves, that doesn't impact sea level because they're floating on water. But of course, this change in the ice sheet behind, this does impact sea level. And it turns out that these ice sheet models have got to simulate some really tricky processes. And some of these are understood quite well, such as this one, the marine ice sheet instability. So what happens is you have slightly warmer water, so just above freezing, and that comes under the ice shelf, and it melts it, and it causes this grounding line to retreat. And in some cases around Antarctica, what this will do, because of the way the seafloor is sloping here, you will end up with a much increased flux of ice from the centre of the ice sheet to the edge of the ice sheet because you're thickening this area here. So this can lead to accelerated loss of ice in Antarctica. This process is very well understood and it's incorporated in all the models. This process is not as well understood, And this process, the marine ice cliff instability, or MECI as it's called, so again, what's happening is we lose these supporting ice shelves, and in some cases around Antarctica, we could be left with these enormous cliffs of ice. And when I say an enormous cliff of ice, I mean it. Just picture in your head for a minute a cliff of ice 1 kilometre tall. A kilometre tall. Now, a lot of that is underwater, but you still have 100 metres of ice above the surface, and you can have this hydrofracturing process driven by these little bits of melt on the top. This means that this cliff is inherently unstable. And so some ice sheet models are incorporating this process that basically means once this starts happening and you get these exposed cliffs of ice with hydrofracturing, you can get very fast retreat of the ice sheet. Now, this is fairly controversial because it hasn't been observed in Antarctica, but it has been observed in Greenland. So we have different ice sheet models, and they make different projections for future change. But one thing we can do is test the models with our paleoclimate records. So we can test these models using the last interglacial, so that raised beach in the Gower, as a test. We can use the Pliocene as a test. And when we do this, we find that actually a big difference between the models, or the difference in the models that's really important at the moment that we're just starting to realise this year, is the presence of this marine ice cliff instability, whether you have that in the models or not. And it turns out that 55% of the models that include the process can pass our geological tests, but 51% of the models without this also pass the test. And what this is actually telling us is that our geological test isn't strong enough. So our signal-to-noise ratio is not quite strong enough to be able to discern between these two different models. And these different models have very different predictions for the near future in terms of sea level rise. So this is the contribution just from Antarctica to sea level over the next, over the rest of this century. This is models with MECI. This is models without MECI. In terms of global changes to sea level, these top plots show sea level projections for models without MECI and with MECI, and on the left up to the year 2100, and on the right up to the year 2300. So you can see having this mechanism in your model means that the absolute sea level predictions are revised upwards. So here, this is 2.5 metres by 2100. This is 15 metres on this axis here in our plot that goes to 2300. But we also see this bigger difference between our different RCP scenarios. Now, this, of course, has lots of implications for coastal communities, as well as ecosystems and infrastructure and all the rest of it. But just in terms of coastal communities, this is the kind of numbers of people that will be displaced. So even if we look at the conservative models without MECI, we're looking at something like 100 million people being displaced just by the end of this century. But for policy decisions, we really need to know which of these is correct. Should we have MECI? Shouldn't we have MECI? Some geologists think they found evidence for this process occurring in the past. So they've mapped out the seafloor around Antarctica, and they've said it occurred in the Pleistocene, so we should expect it to happen in the future. Other scientists not so certain. I myself am working with ice sheet modelers to try to really crack this problem. So we're looking at intervals in the past where we know we have huge changes in sea level, so they will provide a much better test of the different models, so we'll have a much bigger signal-to-noise ratio. But I want to finish up by making one really important point. So this is my take-home message. So if you're napping, you at the back, if you're napping, you can wake up now. I'm going to show you this figure. My take-home message is that, yes, there are uncertainties in some of our future predictions, and scientists are working really hard to narrow down these uncertainties. But actually, the most important factor when we're considering what will sea level do in the future, the most important factor is in our hands. It's how much carbon dioxide we decide as the human race to put into the atmosphere. So this graph shows the probability of exceeding 1 metre sea level rise. Okay, so it goes up to 100%, and this is time, so this is going up to the year 2300. So let's think of that business as usual scenario from the IPCC reports. That's shown here in this kind of pink curve and this red curve. Whether or not your models include Miki, the pink curve, or they don't, the red curve, we're going to exceed 1 metre sea level rise, by not too long after the year 2100. But look at the difference between the different RCP scenarios. So we have this pink curve for RCP 8.5, this is RCP 4.5, and this is 2.6 here. This is limiting climate to 1.5 degrees warming. We don't come anywhere near 1 metre sea level rise. And the models without Miki, again, this is RCP 8.5 compared to RCP 4.5. At the moment, we're somewhere in between the blue curves and the red curves in terms of our emissions. Now, what this means is we happen to live in a really critical time. So all the decisions being made globally now are going to have really huge impacts on our future generations, including our children, and including their children. And so I just want to finish by encouraging you, if at all possible, to support the next generation as they fight for a voice in the climate change arena. And with that, well, thank you.
Thank you very much, Carrie. Questions? Why is
Hello, thanks. That was really interesting. I don't understand why Miki should be controversial if it's been observed in Greenland. Is there something about Antarctica that might mean it wouldn't apply there?
Well, it's just because of this recent paper that shows that 51% of the models without Miki pass these sort of geological tests, if you like. So these authors argue that it's slightly too soon to be confident that we need Miki. From my own perspective, I often work deeper in the past than the Pliocene. So I work in the Miocene, where we see much larger changes in global ice volume. And the traditional models, the models without Miki, can't simulate that. So I think that we do need something else in the models. And to me, Miki is a good answer. But I think it's probably need another couple of years of research to really say convincingly one way or the other. The problem is scientists are just so cautious and for good reason. So we're not, even though personally I think we probably do need this, I'm not prepared yet to say definitively that we do yet until we do further work.
Hi, in terms of like global sea level rise, if all the ice sheets supposedly melt, would isostatic rebound of like Antarctica and Greenland cause it to get even higher over time?
Would it cause? No, I don't think so. But what the timescales of the isostatic rebound is really quite slow. So you're talking a few thousand years for that to occur. Whereas we're kind of really concerned, slightly more rapid changes. Well, I don't think that would have a big impact on. You're talking about like the volume of the ocean basins.
Yeah. Maybe because of how far Antarctica has sunk due to the ice sheet being on top of it.
Yeah, I don't think so. Yeah. But that's important consideration for regional changes in climate, obviously. Yeah. Hi.
Yes, thank you very much for the talk. Just one puzzling question. I'm not from the geological kind of background. From the historic record, going back to millions years. And then the fairly recent, with human activities, we see the stats of the carbon content in the air.
Yeah.
I try to make the logical link because the record saying on the Earth's surface only less than 3% of the Earth's surface with human, which is occupied by a human. So how come the human activity in that small space covering the Earth, only about 3%, can have that much significance of contribution to the carbon content in the air?
Well, great question. And I suppose this is one of the reasons why the Geological Society have, picked carbon as their theme. So the whole carbon cycle is really fascinating. But the answer to your question really is due to how fossil fuels form. So if you think about coal, for example, all of the carbon in coal deposits came from the atmosphere. So if you go all the way back to the Carboniferous, had very warm climate again, very high carbon dioxide concentrations, and there was lots of vegetation everywhere. And then that vegetation, was deposited in very swampy conditions, and just, quirk of fate almost, because it was swampy, it was preserved. It didn't rot away and release the carbon straight back to the air again, which is what usually happens. So it was locked away. So the carbon was taken from the atmosphere and put into what became coal deposits. Now, the really key thing is that took millions and millions and millions of years. Okay, so all the time, the atmosphere is being replenished with carbon dioxide from volcanic emissions, for example, but then that carbon dioxide is being stored in these deposits, which we see as coal deposits, and then similar things happens with oil deposits, for example, gas deposits. And then people come along and they burn it. And you're burning coal, you're burning this compressed carbon that took millions of years to cut out of the atmosphere, and we're just putting it straight back in. So that's why we've had such a big effect. And that's why, as paleoclimate scientists, what we would really love to have is an analogue, like a proper analogue of the current rate of forcing. We can't find one. It's really difficult. We just can't find an analogue because there's no natural process that can do what we've done. We've playing this really crazy experiment on our climate system. You would not really choose to do this, but we are.
Any further questions?
It seems like one of the conclusions is that, the policy making is where we need, as a human race, to be putting some focus. So I was wondering what sort of role you and your colleagues and academia play in educating those policy makers who maybe aren't coming along to events like this. How do we get the messages across to the policy makers in a way that's effective?
That was kind of the idea of IPCC. So that's our main route into them. So we do the science, and then some of us sit on the boards that write the reports. And so the IPCC published kind of different sets of reports, some of them quite detailed evaluations of the science, and then simple summaries for policymakers that have that express purpose. But, as I showed at the beginning, they've been doing this for so long and nothing much has changed. And it's only very recently, really, with people like Greta. This is the first time when I've thought things might change in the future, and it's a bottom-up process. And I think it has to be, and people have to take individual actions. If you think about these politicians, are they going to make some quite... They've got difficult decisions ahead of them. It's going to be much easier for them to make those difficult decisions if they can see that they have the support of everyone from the bottom up. So if they see everyone kind of trying to live their lifestyle in a greener fashion, and they see people's protesting on the streets because it means something to them, and these people are concerned about the future, then I think they're more likely to make these changes. I think, us scientists can give them briefing note after briefing note, and I'm yet to see a significant impact of that.
Gentleman in the front here.
Sorry, okay.
Oh, sorry. This gentleman next, so if you could take that question.
Hello.
Hi, sorry.
Hi,
Yep.
sorry. It's fantastic talk, thanks.
Oh, thanks.
One question, at the rate at which things are getting depleted and, Greenland is always in the news past few weeks, I think. So scientists like you, Richard Alley, and people like who are so interested in paleoclimatology, have you made all discoveries that are supposed to be made before even those evidences get obliterated? I mean, the ice core related studies and all that. So my question is, as an earth scientist, all the evidences you have in these ice cores and all, wherever you had to carry out those experiments and get the factual data, have they all been sort of nearly completed, or is there more to do before even those evidences start disappearing? And it'll make it much harder for scientists like you to go back in science. I mean, are we close to that point where even evidences are getting obliterated, is my question.
That's a really interesting question. I don't think so, because a lot of these very long ice cores, they're taken right from the centre of Antarctica, from these domes. So far, we've got a continuous record going back 800,000 years, and there's a big push at the moment to extend that and go back 1.5 million years, and that's because the climate system actually changed about 1 million years ago, and it's a big puzzle in paleoclimate science. So it changed its sensitivity to orbital forcing, and there's a big question: is why did this happen? So there's a big push to actually increase these ice cores. Fortunately, most of them aren't in areas at the moment where we're going to where that ice will collapse. But there's other ice core scientists that work on glaciers, for example, and there's a real push there to core the glaciers around the world. So you can get tropical records of temperature, for example, from these glaciers, and you're right, their lifetime really is limited, and there's a big push to collect those and freeze them while we can. Yeah.
Final question from the gentleman.
Thank you. It's really interesting. One thing that happened was the Industrial Revolution that caused a lot of carbon dioxide. The other thing is the expansion of the world population at the same time. How important is it to reduce the world population?
Oh, what a question to end on, gosh. I mean, some people would say that the population will be reduced as a result of climate change anyway. If you look at countries like India, for example, they're already really suffering from heat stress. I don't really want to comment on the ethics of controlling human population, but obviously, that is a huge problem, and as a human race, we are overusing Earth's resources. That's very much acknowledged. I think, in terms of where to go in future, we need to reduce our emissions and change energy sources, so switch from hydrocarbons to renewables. There's lots of things that we can do and we should do first, I think.
Can we swap places?
Yes, sorry.
Carrie, thank you for fantastic talk tonight, very illuminating and a bit scary, frankly. And actually, when you showed that slide of Doctor Who, it made me think that even as a kid, I found time travel with Doctor Who pretty scary. But I think your journey that you've taken us on this evening into the future in your TARDIS is probably the scariest I've ever listened to. And I think, speaking entirely personally, what I find incredibly frustrating about the situation in which humanity finds itself now is that the science, in my personal view, is very, very well established. We know what we need to do, and yet we carry on as a human race careering at top speed towards this cliff edge and can't do anything about it. And I think it's actually quite easy to become despondent about it, which for me underlines the importance of the work that you and colleagues in the paleoclimate field are doing. It's incredibly important work, and thank you so much for coming here this evening and sharing this excellent work with us. Thank you.